I want you to imagine zooming all the way in on reality. Just keep zooming.
Right. Way past the everyday stuff.
Yeah, past the cells in your body, past the complex molecules, past the individual atoms.
Keep going.
Exactly. Keep going, pushing past the subatomic particles, past the quarks, until you are past even space-time itself.
Which is hard to even visualize.
It is. But when you finally hit that absolute fundamental bottom of existence, I mean, what's left? Is it just empty space? Or is it like pure math?
And that really is the ultimate scaffolding question. I mean, if we manage to strip away every physical law we currently rely on to explain the universe, we have to ask what actually holds reality together, if anything.
Right. So today we're going on a deep dive into a really fascinating recent update from a research group known as the SFHSGP project.
It's a massive thought experiment, basically.
Yeah, they're essentially running this massive test to see if you can build a universe using nothing but tiny recursive mathematical interactions.
Just math. Nothing else.
Just math. We're looking specifically at their May 19, 2026 update, which covers phases 265 through 315 of their work. And okay, let's unpack this, because the core puzzle they're trying to solve is whether complex reality can naturally emerge from simple math without any pre-existing laws of physics to, guide it.
Right. And to set the stakes for what they're testing here, these researchers are using minimal recursive operator systems.
Which sounds very technical.
It does, but they're essentially just tiny mathematical rules that take an output and immediately feed it back into themselves as a new input.
Like a loop.
Exactly like a loop. And they are doing this in a theoretical vacuum. I mean, there is no gravity.
No electromagnetism.
Right. There is no speed of light to act as some cosmic speed limit. It's just the math.
Well, the natural assumption is that taking away all those physical guardrails would lead to, well, absolute chaos.
Pure randomness.
Yeah, because if you have no laws dictating how things should behave, a million unconnected mathematical interactions shouldn't just spontaneously form a coherent structure.
No, they should just generate infinite static.
Right. I mean, if you take a million unconnected puzzle pieces and just dump them on a table, they don't, accidentally fall into a perfect geometric grid.
They really don't, which makes the first major finding of this recent phase so counterintuitive. Because the system completely defied that assumption of chaos.
It actually worked.
It did. The researchers discovered what they call strong low-rank structure.
Okay.
So rather than dissolving into random noise, the system repeatedly collapsed toward a dominant low-dimensional axis. What's fascinating here is that it found an order all by itself.
So let's break down the mechanics of how that actually works, because the update mentions the system demonstrated high PCA concentration.
Right. Principal component analysis.
Exactly. And in data science, if data is purely random noise, it just scatters uniformly in every possible dimension. You can't predict it.
It's a mess.
Complete mess. But if a data set has high PCA concentration, it means almost all the variation is happening along just a few primary pathways.
The math is naturally finding a dominant shape. Yeah.
The dynamics organize themselves into a constrained geometric structure. So instead of exhibiting, infinite degrees of freedom where every point just does its own random thing,
Right.
the interactions mathematically lock together. And the recursive nature of the system is actually what forces this to happen.
Because of the loop we talked about.
Precisely. Because the output of one tiny equation constantly becomes the input for the next, random outliers just get mathematically smoothed over.
Oh, wow.
And dominant patterns reinforce themselves. So it's a self-organizing principle born purely of iteration.
I mean, I see why this is sending ripples through the physics community, because general relativity, which is our best theory of gravity, is entirely geometric.
Entirely.
So seeing geometry emerge spontaneously from unguided recursive mathematics, I mean, that provides a massive foundational clue.
It really does.
It suggests that geometry doesn't need to be imposed by a physical law. It can just be the inevitable result of math interacting with itself. The system is not behaving like unconstrained randomness. It's actively building a structure. But finding a geometric pattern at the absolute microscopic level immediately introduces the problem of scale.
Right, because a shape might exist when you're looking at the absolute finest possible detail, but what happens when you zoom out?
Exactly. Does that structure hold up, or does it dissolve back into static when viewed from a distance?
And that question leads directly to one of the most significant findings in the entire update.
Recursive stability under scaling.
Yes. The researchers tested the system's resilience using this mathematical process called coarse graining.
which is heavily related to renormalization group or RG scaling in
All
physics.
right, let's ground RG scaling mechanically for a second.
Yeah.
It's essentially a mathematical way of deliberately blurring a picture to see if the macroscopic rules change when you ignore the microscopic jitter.
That's a great way to put it.
You group small components together, you average out their behavior, and you see if the new larger component still operates by the same fundamental rules.
It's a very precise way to visualize it. And in actual physics, fundamental laws need to survive that blurring process.
Like thermodynamics.
Exactly. The laws of thermodynamics hold true whether you're looking at the behavior of a small thimble of gas or a massive, sprawling interstellar nebula.
The physical rules scale.
They do. So when the researchers coarse-grained this mathematical system and averaged out all those tiny recursive details, they found that the fundamental structure absolutely survives.
That's incredible.
The structural relationships between different sectors persist, and the organizational geometry remains highly correlated.
It operates a lot like a digital map, honestly.
Oh, how so?
Well, when you're zoomed all the way in on a city map, you see the intricate details, right? The tiny alleys, the individual houses, the local stop signs.
Sure.
But when you zoom out, those microscopic details blur together into neighborhoods.
Right.
And you zoom out further, and the neighborhoods become a single dot on a state map. The tiny features vanish from your perspective, but the overall shape of the city, the major highways connecting it to other areas, they still make perfect functional sense at every level of zoom.
The structural highways remain intact even when you stop rendering the driveways.
Exactly.
And this scaling stability is crucial because it mimics a major behavioral feature of actual physical laws. But we do need to draw a firm line here.
Fair enough.
This scaling stability is entirely a mathematical property at this stage. The project has not derived actual physical laws. They have not proven that this recursive math is the secret blueprint of our specific universe.
So they've shown that this system behaves in a way that mimics the style of physical laws without necessarily containing the substance of physics yet.
Yes.
It's the structural scaffolding of reality without the physical stuff.
Right. We must be careful not to conflate mathematical elegance with physical reality. It's a highly suggestive parallel, but it remains an analogy.
Well, let's follow that map analogy a bit further anyway, because a perfectly uniform city where every single block looks exactly the same is incredibly boring.
And practically speaking, trivial.
Right. For a universe to actually generate complexity, things like stars, planets, chemistry, biology, the components have to be distinct.
They have to do different things.
If this mathematical system just scales up into one perfectly uniform, repetitive geometric block, it's not a universe. It's just a crystal.
A completely uniform system is mathematically trivial. You need components to differentiate from one another to create anything of value. But that introduces a serious mechanical paradox into the system.
How so?
The moment localized areas of math start behaving differently from their neighbors, you risk breaking the overall geometric structure. You risk falling back into the chaotic static we just established the system avoids.
Oh, I see. So the system has to find a way to get distinct features without shattering the underlying geometric stability.
Exactly. And it handles that tension through a mechanism the researchers call stable differentiation.
Which was the primary focus in phases 314 and 315 of the research.
Yes. The framework naturally generates persistent organizational sectors that perform entirely different mechanical roles within the larger system.
And the update lists three main types of these sectors, right?
It does.
You've got projection sectors, anti-symmetry sectors, and neutral sectors. Functionally, projection sectors act as the builders. Their mathematical role is to preserve and extend the organization of the geometry.
But if a system only has builders, the structure just grows infinitely dense and rigid.
Right, which is where the anti-symmetry sectors come into play. They act as the necessary counterbalance to the projection sectors.
Right.
Looking at the mechanics of the anti-symmetry sectors, they function remarkably like noise-canceling headphones.
Oh, that's interesting.
Yeah, they aren't just randomly destroying the structure, they're generating an inverse mathematical wave to the structure being built by the projection sectors. They create destructive interference to actively suppress overorganization.
So the anti-symmetry sectors introduce controlled negation. They prevent the crystal from growing infinitely. And situated between the builders and the suppressors, the system generates neutral sectors.
The third type, right?
Right. Their specific mathematical job is maintaining metastable continuity. They essentially act as the diplomatic buffers, ensuring the constant conflict between projection and anti-symmetry doesn't tear the entire network apart.
So the interaction between these three distinct sectors creates what the paper terms bounded divergence. The system successfully creates distinguishable structures, differentiation, but the divergence is strictly contained.
It doesn't cause catastrophic instability.
Right. The math manages to find the exact sweet spot between a boring, rigid structure and total chaotic noise.
And we see this exact type of bounded divergence in the structured interaction regimes of real-world mathematics and physics. Complex systems rely on competing forces maintaining a dynamic equilibrium.
Always.
Again, there's no direct mapping to known physics yet, but demonstrating that unguided recursive math naturally develops differentiated, stable sectors is an incredible achievement in emergent organization.
Honestly, reviewing this architecture, a low-rank structure, avoiding chaos, scaling stability that mimics thermodynamics, and sectors generating bounded complexity.
Yeah.
I mean, it's very tempting to conclude these researchers just found the source code of reality.
It is tempting.
But there is a vital section in this update titled The Honest Assessment, and it provides a very necessary, sobering reality check.
Because failures in theoretical mathematics are frequently more illuminating than the successes.
Yeah.
And the researchers are incredibly transparent about what this framework utterly fails to do. It does not prove idealism is true. It does not prove consciousness is a fundamental property.
Important distinctions.
And it has not derived quantum mechanics, and it has not derived general relativity.
Right. It hasn't yielded a single actual physical constant. There is no derivation for the speed of light, the mass of an electron, or the Planck lengths.
Nothing like that.
But beyond missing the numerical constants, it's missing fundamental mechanics. And the failure that stands out most is the inability to show locality emergence.
This is a big one.
Because if this is purely recursive math happening everywhere at once, we have to ask how the system handles distance.
Currently, it doesn't handle it at all. And if we connect this to the bigger picture, that is a massive hurdle. Locality is the foundational principle that an object is only directly influenced by its immediate adjacent surroundings.
Right.
For a star to exert a gravitational pull on a planet, that force has to propagate through the physical space between them at a finite speed.
Right. There is no spooky action at a distance. If our sun suddenly vanished from existence, we would still orbit empty space for 8 minutes because the gravitational change and the lack of light take time to reach us locally.
Exactly. And because this mathematical system didn't naturally generate locality, it implies the recursive interactions can influence each other globally without respect to any emergent spatial distance.
Everything is just immediately connected.
Right. The entire network is entangled in a way that violently contradicts how our physical universe actually operates.
And the system also failed to show action or geodesic behavior, right?
Yeah. Yes. And the principle of least action is another absolute cornerstone of modern physics. It states that nature is inherently lazy.
Lazy?
Yes, a physical system will always evolve over time in a way that minimizes a specific mathematical quantity called action.
So it's the universe's way of taking the path of least resistance.
Precisely.
Like, human behavior mirrors the principle of least action constantly. When we cut across the grass in a park, instead of walking all the way around the paved sidewalk, we're minimizing our energy expenditure. We take the geodesic.
That's a great real-world example. And whether it's a planet orbiting a star, a thrown baseball moving through the air, or light bending around a black hole, they all follow geodesics, the most efficient energy-minimizing path through curved spacetime.
But the math didn't do that.
No. The fact that this recursive math framework does not naturally fall into action-minimizing behavior means it's missing the core driving mechanism of physical movement.
Wow. And the update also notes a failure to find simple temporal ordering. The map does not naturally produce a one-way arrow of time.
Right.
So if the system lacks spatial distance, lacks the mechanism for physical movement, and lacks the forward flow of time, I mean, we're clearly not looking at a replacement for our current physics textbooks.
We are operating strictly in the realm of pre-foundational mathematical structure. The researchers explicitly state the framework is not close to replacing physics. It's a brilliant demonstration of organizational geometry, but tying it to physical reality remains a highly speculative endeavor.
Okay, so if the system fails on locality, fails on action principles, and fails on time, we have to ask why this research warrants such deep focus. What makes this specific mathematical sandbox so important if it doesn't accurately describe our universe?
It matters entirely because of the underlying hypothesis driving the SFH-SGP project. The ultimate goal is to explore whether known physics is actually the deepest layer of reality.
The proposal is that there's a foundation beneath spacetime itself.
Exactly. Quantum mechanics, fields, particles, and relativity might just be the macroscopic symptoms of a much deeper, purely relational geometry. The underlying math doesn't look like physics because it exists at a layer before physics has even been generated.
Right. A helpful mental model for this is a video game engine.
Oh, I like this.
Yeah, when you're playing a game, the fundamental rules of your reality are gravity, object collision, and how fast your character can run. Those are the physics of that specific digital world.
Sure.
But if you crack open the software and look at the source code, you don't find tiny digital gravity or tiny physical objects. You just find pure binary code.
Just math.
Just mathematical logic feeding into itself over and over to generate the illusion of a three-dimensional world with rules.
And the physics of the game emerge entirely from the math of the code. This research is testing whether our universe operates on the exact same architectural principle.
Right.
Under this paradigm, physics isn't fundamental at all. It emerges from stable, recursive geometry.
And this philosophy aligns heavily with fields like quantum information theory, emergent gravity, and tensor network spacetime. There's a growing consensus across multiple disciplines that space and time might just be emergent properties of a non-spatial, non-temporal network of mathematical relationships.
What this update proves, despite its documented failures with locality and action principles, is that purely unguided, minimal relational rules can repeatedly produce stable, recursive structures.
It's proof of concept.
Exactly. Showing that genuine complexity and stability can arise from pure mathematical iteration without devolving into chaotic static is a profound contribution to systems theory and information geometry. It proves the architectural concept is possible.
Let's bring this all together. We started by looking at a system of tiny mathematical interactions that, against logical expectation, avoided chaos and formed a low-rank